क्लास हम लोग अब फिर से इलेक्ट्रोस्टैटिक्स स्टार्ट कर रहे हैं गॉस लॉ बेटा। और हम लोग बहुत सारे सवाल करके आए हैं कूलम्स लॉ के, इलेक्ट्रिक फील्ड के, डाईपोल के, और अब गॉस लॉ से इलेक्ट्रिक फील्ड कैलकुलेट करना सीख रहे हैं, ठीक है। एंड लास्ट लेक्चर वी स्टडीड, वी लर्नड दैट electric flux is nothing but lines of forces, and lines of forces, number of lines of forces penetrating an area is electric flux, right? Then we learned that number of lines of forces penetrating an area depend upon three factors. One, strength of electric field. More is the strength, more will be number of lines. Second, size of area. If area increases, the number of lines penetrating that area will increase, and orientation of that area with respect to electric field. If orientation changes, the number of lines penetrating that area also changes. Do you remember that if area is perpendicular to the field, see, if area is perpendicular to the field, then maximum number of lines passes. So we can say that this is maximum flux associated with this area. And if the area, surface area, becomes parallel to the field, then no line penetrates the area. So actually flux linked with the area, or flux penetrating the area, becomes zero. That means what? The orientation and relation of the flux is such that flux is actually proportional to cosine of the theta. And remember, pay attention that theta is here angle between electric field and area vector, not electric field and surface area, but area vector. Actually, we devised area vector because the area and its direction, its orientation is changing the flux. So actually we defined area, we treated area as a vector, and we said that area vector is always perpendicular to the area, perpendicular to the surface. If it is an open area, for example this rectangular surface area, then area vector is perpendicular to the surface area. But here you have a freedom that you can take this area above the surface area or below the surface area. The only condition is that it should be perpendicular to the surface. But if it is a closed area, for example this is spherical shape surface area, or a cube or a cuboid, then area vector is always not only perpendicular to the surface, see, not only perpendicular to the surface, but also coming out of the surface. Getting it? So area vector for a closed area is always coming out of the surface and perpendicular to the surface. So depending upon the type of area, we have to define our area vector's direction. So now come to finally the Gauss law. What Gauss law says? Understand it. Just relax and listen to me carefully. Gauss law says that net flux coming out of a closed surface, that means Gauss law is defined for a closed surface. Net flux coming out of a closed surface is equal to charge enclosed by the surface upon epsilon naught. Epsilon naught represents the medium. If the medium is air or vacuum, then epsilon naught. But if the medium is anything else other than air or vacuum, then this will become epsilon naught K, where K is relative permittivity. So, flux coming out of a closed surface. See how we write it in mathematical form. I have taken this spherical surface because here charge is distributed on the surface because it's a conductor. I have taken a spherical surface. It can be a spherical shell which is non-conductor, but since it is a shell, so if you provide charge uniformly on the surface, it has to reside on the surface only. And if it is a metal, then you will come to know that as soon as you give charge to a conductor, it rushes to the outer surface and stays on the outer surface only. So listen to me carefully again. The spherical surface, if it is a conductor, then charge will be at the outer surface only. In conductor, no charge can reside inside the conductor. And if it is non-conducting material, then consider it as a spherical shell. That means it's a shell and it has only outer surface. So the charge will automatically will reside on the outer surface. So whatever discussion we are going to do, that is applicable to metal conducting spherical surface. And if a not conducting surface is there, then it's a spherical shell. Anyway, we have to discuss it later on once again. But right now I am going to understand we are going to understand the Gauss law only. So just look at the charge distribution. It is uniform on the surface only, right? Now see, electric field of discharge distribution will be like this, radially outward. We will discuss this condition later on. But right now, you take it from me that electric field will be radially outward. And area vector and electric field both will be perpendicular to the surface area. So just come to this point. At this point, area vector is perpendicular to the surface area at this point. And electric field vector, electric field line will also be perpendicular to the surface. So actually, electric field and the surface vector, area vector, both are parallel to each other at this point. And this case will be same if you take the area vector here, if you take the area here. But can you see that I am considering a very small area element? Why? Because electric field is radially outward. It is uniform, not uniform, that means magnitude of electric field is same at the surface. It is radially outward, but at different area elements, the direction of field is changing. So we have to take a small element, area element, and only there we will consider what is E, what is direction of area vector at that point, and what is flux, little flux passing through that element area at that point. because electric field is changing here at every point its direction. So we have to consider a small area element. We have to consider at that point area vector's direction, electric field line's direction, and angle between the two, and then element area and its flux. Whatever flux is associated with that element area, that we will calculate first. Once we calculated the flux associated with this element area, then we will integrate it for the whole surface. That is the way how to calculate flux associated with this spherical surface which is uniformly charged, right? Now why we are calculating flux? Because Gauss law is saying that net flux which is coming out of this closed surface is charge enclosed by the surface upon epsilon naught. So if we have to apply the Gauss law, and why we are going to apply the Gauss law? Because we want to calculate electric field using Gauss law. So why not Coulomb's law? Why we are interested in using Gauss law to calculate electric field? Because Gauss law makes the calculation of electric field simple. We will see it in different examples. But the condition is that although Gauss law is applicable everywhere, but we can calculate electric field using this law in symmetrical situations only. So Gauss law makes the solution easy, but we are forced to use this formula, this law in symmetrical situations only, because there only we can find the electric field vector, area vector, and relation between the electric field vector and area vector easily. So that is why we have to understand the Gauss law, but along with the conditions associated with the Gauss law, right? So we have taken element area, we have taken electric field at that area, we have taken area vector at that element area. We have seen that area vector and electric field are parallel to each other at that point, and then we said that okay, flux, what is flux? Flux is electric field vector dot area vector. That we have discussed in the last class. Now here we have taken since element area, so we have written it E dot dA. Now open it, E dA cos theta, where theta is angle between electric vector and area vector. Let me remind you again, theta is not angle between electric vector and surface area. It is angle between electric vector and area vector, right? So we said okay, E dA cos theta, and here it's magnitude of E and magnitude of dA cos theta. But theta is here 0 because they are parallel to each other. So in this case, E dA cos 0. But right now we are not going to solve it for a spherical surface only. We are just understanding what is Gauss law. So we just take it as a concept that okay, this is the way to calculate flux. Once we calculated flux, then let me come to the statement again. What is the statement? Net flux coming out of a closed surface. That means they are not talking about element area, they are talking about whole closed surface. So E dot dA, which is flux associated with element area, when it is integrated over the closed surface, check this symbol I am using here. This symbol says that this is integration over closed surface. And after writing integration sign here, this is now area, net area, this is now flux, net flux coming out of the closed surface, which we have taken here as spherical surface, right? Now let we again come to the statement, net flux coming out of the closed surface. We have written net flux coming out of the closed surface. Now they are saying it is equal to charge enclosed upon epsilon naught. Now here the main point is charge enclosed by the surface upon epsilon naught. Which surface? It's a Gaussian surface. Understand it now. Actually, when we say net flux coming out of a closed surface, the closed surface is called Gaussian surface. Now you will think, what is Gaussian surface? Gaussian surface is a closed surface area which passes through that point where we are supposed to calculate electric field. Listen to me again. Gaussian surface is that surface area, closed surface area, which passes through that point where we are asked to calculate electric field. And that surface area or the Gaussian surface must have two conditions. First, that it should pass through the point where E is supposed to calculate, to be calculated. E is supposed to be calculated. And second condition, Gaussian surface should be closed. And third condition, that this Gaussian surface should be such that either E is constant over this surface throughout, or this Gaussian surface should be such that this electric field is perpendicular to the surface. That means, what surface we are talking about in the law? We are talking about Gaussian surface. And what is Gaussian surface? Gaussian surface is a closed surface which passes through that point at which we are supposed to calculate electric field. And this Gaussian surface is always taken such that either electric field is constant over the surface or electric field is perpendicular to the surface. If electric field is constant throughout the surface, then we have advantage that we can take the E out of integration, which is in the term flux. And if E is perpendicular to the surface, then this E dot dA will be 0. And thus we simplify the calculation of electric field. So again come to Gauss law. Gauss law says that net flux coming out of closed surface, we have written net flux coming out of closed surface. This is the left part. And then charge enclosed by the surface means charge which is inside the Gaussian surface upon epsilon naught. This integration is called surface integration of electric field. Let me take introduction of each term used in the Gauss law. What is that part? This integration is called surface integral of electric field, and it represents this integration. This left side expression represents net flux coming out of the closed surface, which is known as Gaussian surface. Then this area is element area of Gaussian surface, right? And this charge enclosed is that charge which is inside the Gaussian surface. And epsilon naught, as I said, is representing the medium. So finally Gauss law is net flux coming out of the closed surface, that is Gaussian surface, is charge enclosed upon epsilon naught. This is Gauss law, and it says that surface integral of electric field is equal to Q enclosed upon epsilon naught. Now the question is, what is Gaussian surface and why is it required? Gaussian surface, as I have already explained you, is a closed surface passing through the point where we need to calculate the electric field. Now why it is required? Because beta Gauss law is a mathematical concept which is used to calculate the electric field of physical situations. So in this mathematical concept, we have to follow the steps, few steps in every case, and in those steps the first step will be select a proper Gaussian surface, right? Gaussian surface, let me quickly remind again. It is closed, it is passing through that point at which we have to calculate electric field, and the shape of the Gaussian surface should be such that either electric field is constant over the surface throughout, or electric field is perpendicular to the surface, right? Now before we apply this Gauss law on different cases, let me feel the important concept related with the Gauss law. The first concept is, that in this case I am taking three charges to be present in the space, Q1, Q2 and Q3. And I was asked to calculate electric field at P, right, due to all the three charges. Now mathematical concept of Gauss law says that first select a proper Gaussian surface. Let me select this Gaussian surface, blue shaded surface, right? It's a closed surface, okay? It is passing through P, yes, which is our condition, and it encloses only two charges out of three. Doesn't matter. Here is this concept which we are required to understand clearly. What? That in this case, when we are going to calculate flux coming out of the surface, and which is equal to Q enclosed, when we will calculate electric field using this expression, the electric field will be resultant electric field due to all the three charges. Getting this point, electric field on the left hand side, that will give you resultant electric field due to all the three charges. This question was asked once in NEET. But when we are substituting Q enclosed, that will be only those charges which are inside the surface, that is Q1 and minus Q2. So you got the 2 points. Q enclosed is only the charge which is inside the Gaussian surface. But that will not affect the result. Electric field will be resultant electric field because of all the three charges. Although the substitution of the charges here is only those two charges which are inside the surface. So this is first concept which you should be cleared. Second concept. If electric field is 0 at every point of the closed surface, assume a condition when electric field is 0 at every point of a closed surface. If this is 0, then certainly flux coming out of the surface will be 0. Yes or no? Then according to Gauss law, if left hand side is 0, this epsilon naught is not 0, you know, then left hand side is 0 certainly implies that Q enclosed is 0. So, if electric field at every point of closed surface is 0, that implies that net flux coming out of the surface is 0, and that implies that charge enclosed is 0. But if net flux through a closed surface is 0, see how I changed the statement. This statement is very important for entrance exams, mains and NEET. They ask you this question in objective questions using the concept, and sometimes directly they will ask you the same thing. If electric field is 0, that certainly means electric flux is 0 and charge enclosed is 0. But if net flux through a closed surface is 0, then it does not imply that electric field is 0. Getting the difference of the two statements? We will see this in the next point. That's why I am saying that if net flux is 0, then also the electric field may not be 0. So let me see the next conceptual point, and that is this one. See, if charge is outside the closed surface, that means no charge is inside the closed surface, and we have taken three different cases. Here the surface is spherical and charge is at infinity. You know that if charge is at infinity, so the lines of forces, we already discussed it in lines of forces topic, that lines of forces will be parallel to each other. So whatever flux is entering the closed surface, the same flux must come out of the closed surface. Yes or no? So flux moving inside can be taken as negative. Then flux moving outside will have to be taken as positive. And if three lines are entering and three lines are moving out, net flux will be algebraic sum of the two. One is negative and one is positive. And whatever flux, whatever number of lines entered the closed surface, the same number of lines exit the closed surface. So automatically the algebraic sum will become 0. That means if charge is outside the closed surface, always the situation will be like flux entering and flux exiting will be same. and they will result in zero flux. So see here, electric field is not zero, but net flux associated with the area is zero. This can be understood by the mathematics also. As I said that when you decide the Gaussian surface, then we have to draw E vector and A vector. This is E vector, that is direction of field lines, left to right. But area vector is always perpendicular to the surface and moving out of the closed surface. So check it out. E and DA are opposite to each other. Angle between them is 180 degree. So E dot DA at this point will be E DA cos 180. That means minus E DA. But if you take this side, DA will have its orientation coming out of the surface and perpendicular to the surface, while electric field is still in the same direction, left to right. Now you can see that electric field and area vector are here parallel and angle between them is 0. So E dot dA will become E dA cos 0 and that will become plus E dA. So what is a net flux? Net flux is algebraic sum of the two. So minus E dA plus E dA means 0. So you can understand logically and you can understand mathematically also. Come to second case. Here Q is not at infinity, it is at a finite distance. Now if three lines are entering, the three lines must have to exit. So again with the same logic, the flux entering is equal to flux exiting and net flux through the surface is 0. The same is here. Net flux through the surface is 0. But in all the three cases, see, electric field is not 0. So flux is 0 does not mean that electric field is certainly 0. But if electric field is 0, then certainly flux will be 0. Got this point? Now come to the next point of concept. What is that? If charge is inside the closed surface, right, then it does not matter where the charge is placed. That means take all the four cases. It's a cube, it's a sphere, and it's a hemispherical surface. And charge is inside the surface. But here charge is at the left side, here charge is at the center, here charge is near the lower surface, and here charge is at some random place in the cube. But position of charge does not change the flux coming out of the surface. Now you will think that how is it possible? So let me give you a very good idea through which you can easily understand it. Electric field is nothing but energy, and electric lines of forces are measure of that energy, right? Now take the example of bulb, which is giving you light energy instead of charge, which is maintaining an electric field and spreading electrical energy. You take charge equivalent to a bulb. Now think, if this is a transparent spherical surface, you place the bulb at the center, you place the bulb anywhere in the sphere. The light energy coming out of the sphere will remain same. जितनी लाइट बल्ब एमिट करेगा वो सारी लाइट को स्फेरिकल सरफेस से बाहर आना होगा. तो स्फेरिकल सरफेस के अंदर बल्ब यहाँ है, यहाँ है, यहाँ है, it doesn't matter. And not only this, just think it once again. अगर चार्ज यानी कि बल्ब हमारा सेम रहे तो जो लाइट स्फेरिकल सरफेस से बाहर आएगी और जो लाइट क्यूब से बाहर आएगी वो भी तो सेम होगी. अगर आप बल्ब को जिस सरफेस से घेर रहे हैं वो स्फेरिकल है तो भी उतनी ही लाइट बाहर आएगी जितनी बल्ब पर सेकंड दे रहा है और वोल्टेज के हिसाब से अपनी. और अगर आप उसको क्यूबिकल शेप के कवर से घेर दे तो भी बल्ब जितनी लाइट, जितने जूल्स पर सेकंड एमिट कर रहा है वो सारी लाइट उस क्यूब से भी बाहर आ जाएगी. तो फ्लक्स कमिंग आउट ऑफ द सरफेस actually does not depend upon the shape and size of the Gaussian surface, and it does not depend the position of the charge inside the surface. Are you getting the point? These are very important concepts. You must go through this class once again and grab all the points, write all the points so that when you are solving the numericals and logical questions of Gauss law, you are not getting confused by the language of the numericals and conceptual questions. So in the next class, I will start electric field, how to calculate electric field in different cases. So till then, go through the first and second lecture of Gauss law. That is, I think, 18th and 19th lecture of Gauss law, and get it clear so that when we are applying it on the numerical and conceptual question, you are not getting confused, right? Till then, keep working hard. मंजिल से पहले आराम नहीं करना है. All the best, class.